Hello and welcome to another tutorial on dev.java, and we were looking at the primitive types, and we said that booleans are special types with only evaluate to true or false. And we said that JVM is not, the Java language specification is not very specific or clear about what the size of a boolean variable should be, so it's up to the JVM implementation. And then we looked at the interesting example here, and we saw that we saw that a nice lesson to learn is that whenever you define a local variable to do some calculations with it, and you are sure that the value that this variable holds is not going to change, define it as final, because then when this variable is involved with expressions that involve some literals like integer literals or whatever, then the Java compiler can actually deduce the value at compile time. Now if I bring back the bytecode of this class of the main method that we have here, we saw that the JVM that I'm using, which is the hotspot JDK from Oracle, it pushes for each boolean variable, it pushes an integer to the stack, right? So it actually, what happens here is that it pushes a 4-byte integer. And we said that it doesn't matter if you, because JVM is a stack-based implementation, it doesn't matter if you push one byte to the stack or 4 bytes, because they both of them require 1 byte code at least. That's why the speed is the same. So they just decided to at least in this implementation, they are pushing a integer I constant 0. And the reason that we said that these two lines, I const 5 and then I store 1, is basically it loads this integer literal, pushes it to the stack, and then creates a variable, or basically pushes or stores this value in the first location of the stack, index 1, which holds the address of some memory in Java heap, right? And then we said that next is this operation a equals 7, because when you have the assignment, the JVM first evaluates the right hand side and then stores that in the stack, and then looks at the variable definition on the left hand side and then assigns the previous value to this variable. And we saw that here, after we declared a as final, suddenly there is no extra calculation here. In the bytecode, we are just loading 0, which means false, which means that the Java compiler was able to actually work out what the value of this expression a equals 7 is going to be at compile time, because a is final, its value is never going to change in the scope of this method, right? But then we saw that we still have this condition variable, and after we store it to the stack, we then load it again when we go into this if statement, right? So this was still treated as variable. Now what happens if we also declare this condition as final? Now you see that everything was completely worked out at basically compile time, because you see we load 5, assign it to a variable a, and then load 0, which means the Java C was able to work out this expression a equals 7 at compile time and deduce that it's always false. It stores it into this variable, but then there is no if, there is no check on the condition, because at compile time, because this condition is also final, at compile time Java compiler realized that the value of the condition is never going to change and it's going to always be false. So there was no reason to add any extra bytecode for this else. This condition is going to always be false at runtime, because these variables are final, their value is never going to change. So when you give strong guarantees to the Java compiler is actually able to work out what the values are going to be at compile time, and this could help a lot in optimizing your code. Obviously in Java's philosophy, these optimizations are preferred to be basically deferred at runtime and use the JIT compiler. But again, the best practice is always declare local variables as final, unless you need to change their values. Most of the time actually we define variables and they hold some value and we never change or reassign values to them. They're just easier to work with. Basically, if I want to use number 5 here, it's better to define it as a variable that has a nice name and then use that variable everywhere else instead of trying to just type 5. Hard coding literals in your source code is a bad practice. So local variables, define them as final unless absolutely necessary. That you same with the parameters of a method or the arguments. Again, one of the best practices is that define them as final unless you know that you're going to change them. And note that this is final thing, and compiler being able to work out the values at compile time normally only applies to primitive types. If you have an object reference, obviously even if the reference is final, the state of the object can change. So if you are retrieving a field from that object, unless that field is also final, then the compiler is not able to work out the actual values. But for primitive types, definitely define the local primitive variables as final unless you know that the variables are going to be reassigned or the values in those variables are going to be changed. Because you see, now obviously the Java compiler couldn't work out the fact that we're not using a and condition anywhere else in this method, so it still added some 4 lines of bytecode which for these 2 lines that are not being used anywhere else in this method. But then it worked out the fact that this if statement is unnecessary because of the value that this condition holds. But when this goes to the JIT compiler, obviously the JIT compiler can also see that these 2 lines are useless. Therefore, JIT compiler, when it recompiles and tries to come up with the optimized code, it also removes these 4 lines of bytecode, right? So there are levels of optimization implemented in Java, and it's up to some part of it is up to the user using this final, so that the Java compiler can work out some stuff at compile time. But then most of the stuff are deferred to the runtime and put on the shoulders of the JIT compiler. All right, let's move on from Boolean and go to the char. Again, char is a primitive type that is supposed to represent characters, and we said that Java decided to go with 16-bit Unicode characters or UTF-16. And then both in the source code, actually in the source code, I'm not sure how Java handles the character representation inside the JVM, and I think they have some sort of extended UTF-8 characters. So JVM internally supports UTF-8 because 1-byte characters is the most efficient way of storing character data in the memory. But then for example, for English alphabet, you don't need 2 bytes for each character. You only need 7 bits, not even 1 byte, right? Because English character is basically encoded in ASCII. UTF-8 supports ASCII, so there is no need to have 2 bytes memory wasted on an English character, right? So I believe Java at runtime JVM decides how to operate based on what kind of string literals are used in your source code. If it's just English or numbers, it tries to use 1 byte or basically some sort of compactness so that it can optimize the memory better, right? But by default, at least in your source code, you can assume that the characters are 2 byte UTF-16. And we usually represent them if we want to specify a Unicode character, which is not an English character, we use \u, that's the escape sequence. And then we use the hex representation. And each one of these is 4 bits, right? Hex is base 16, which means you go from 0 to 15 or 4 bits. So each 2 characters here is 1 byte, 8 bits, and then 2 bytes is 16 bits, right? So Unicode characters go from 0000 to FFFF, or 65,000 characters, right? And then now, unlike C++, which character maps to an signed integer, in Java, I think character maps to an unsigned int. So we can actually test that also. So let me just create a new method here. Public static void test2. And we're going to copy all these codes inside here. And then let's look at a character. So char C1 is A, right? And we do sysout on C1. Let's see what we get. and we get A. So what happens if we actually assign a character A to an integer? Now obviously there is an implicit type conversion happens, implicit type conversion happens, and what you do realize is that characters are encoded in bits, right? So bits, and then bits like 2 bytes or 16 bits, they fit very well in an integer type. So if I set this to short, this still works because this character holds 2 bytes, and 2 bytes can fit in short. What about 1 byte or 8 bits? This also converts fine, because this character A probably, so English characters already are encoded in ASCII, which is 7 bits or basically less than 1 byte. So the compiler realizes that this A will fit in a byte integer. So yes, 97. So a small a, 97, capital A, I think there is a, let's create another one. Between capital letters and small letters, I think there is a constant distance. I think it's about 30 or 32. Let's try that. So 65, and let's look at the difference. So C2 minus C3, 32. And this holds true for all the ASCII characters or English alphabet. If you have a lowercase letter and you want to, for example, convert it to uppercase, regardless of what that character is, so you don't need to, obviously one inefficient way is to create a lookup table, right? And then whenever a character is passed to your method, you search that lookup table and see what's the capital version of that. But that's a very inefficient way. So the way algorithms implement like converting a small or lowercase letter to a uppercase, they basically, we can actually try that. So let's say public static char to uppercase, right? Something like that. And we pass a char C, and we want to convert it to uppercase. All we have to do is basically say that we can convert it to an integer. Here I'm assuming it's a lowercase English, so I convert this to byte, right? And then subtract 32, and then convert it back to char. That's it. And semicolon here. This is the most efficient way of converting a lowercase English alphabet to uppercase, because if you look at the ASCII table, there is a constant distance between all the lowercase and uppercase letters. So we can do that. So efficient way is, so inefficient way is like you create a switch expression, and then based on the character you check them to find which character is passed in, and then you find the equivalent uppercase. But here the efficient way, we don't care what the character is, because we know that there is always a constant difference. So let's do a sysout on to uppercase, for example, a small a. It's capital A, and then let's randomly, let's say W, a small w, and capital W. We can try other letters, for example, a B, for example, B, capital B. So this is the most efficient algorithm for converting a lowercase English alphabet to an uppercase, right? And these alphabets have a specific range. A capital A starts from 65, and then we have, I believe, 26 letters, right? So we can see, for example, byte C4 is capital Z. This is the last letter, and then sysout C4. Let's see what the capital Z is, 90. So capital letters, capital English letters go from integer 65 all the way to 90. which means there are 25 characters, right? Or 26, right? From 65 inclusive to 90 inclusive is 26 letters, right? And we are dealing with them as integers because it's very easy to deal with them. But then in general, you can also actually look at their hex. And let's see, I think we can directly convert these. If I look at the byte dot to unsigned int, I think the integer class to hex string can convert integers to hex, so C4, and this gets an integer. A byte can be converted implicitly to integers, so no problem. And 5a, right? So the hex representation of or the ASCII representation, or the 1 byte representation of C4, which is Z, is equal to 0x5a. This is 1 byte. In the 2 byte version, the upper bytes are 0, right? This 1 byte is 0, 5a. What about so hex, what about capital A? So it's C2, um, 61, right? So it's 0x0061. So from 5a to 61, we know that a means 10 in decimal, and then there are up to f, there are 5 more, and then basically, so from 61 to 5a, so C4 Z, and then C2. Okay, no, sorry, I have to use C3, which is capital A. 5a 4 1. All right. So from 1 to F, from 4 1 to 4F, we have 15, and then from 0 to A, which is 10, we have 25. So 26 characters or 26 numbers from hex capital A to capital Z. And the nice thing, the reason that this algorithm works is because in the ASCII table, all these capital letters are one after another, and then all the small letters are also one after another. That's why this very efficient calculation for converting a character to uppercase works very nicely. Now, obviously, if you want to convert a capital letter to lowercase, you just add this 32 to it, right? And note that these type conversions don't require any bytecode or anything, right? Because these are just something that the Java compile. These are just the bits in the memory and the way they're going to be interpreted. And it's also best to, I guess, declare these as finals. Again, best practice is that if you're not going to, this is C, the parameter or the argument is treated as local variable. If you're not going to change the value that is passed in, just declare it as final, right? So let's run this again. Works. So I hope you really understand what the English characters, how they're working, how they're encoded. We need 7 bits, not even 1 byte. Remember, if you look at the bits here, 5a is so a is 10, 4 bits. So 1 2 3 4 for these 4 bits are for 5, and then 1 2 3 4 for a, right? So 10 is 1, which is 8, and then a 2. And the rest is 0. This is 5. And what is a 5? 5 is 1 here and 1 here, which is a 4. And you see the last character is always 0. So because English alphabet is encoded in the ASCII, which is 7 bits, you don't even need 8 bits. And these are unsigned, and basically the last bit doesn't matter. I mean, in C++, obviously the last the char type represents signed integer, so it's some sort of integer type, and that's why the last bit could indicate the sign. But in Java, the last bit doesn't matter because char is strictly used for character encodings, right? So let's try our 2 lowercase. So 2 lowercase and then C4 or capital A, for example. Yeah, so lowercase characters come after the uppercase characters in the ASCII table. You can just Google ASCII table and look at the numbers, or you can just play in Java with the source code. Assign the characters as bytes, or English characters as byte, short, int. English characters are supposed to fit in 1 byte, so they can be assigned to any primitive integer type that Java supports. And then you can use the integer class to hex a string, and then look at the hex representation of them, or directly look at the integer representation of them. And you can use this very efficient algorithm to convert to uppercase and lowercase. So this 32 number is the distance between a uppercase letter and a lowercase letter in the ASCII English alphabet, right? So this only works for the English alphabet, only for English alphabet. All right, so let's move on from characters. In addition to the 8 primitive data types listed above, Java programming language also provides a special support for character strings via the string class. So a string is not a primitive type. A string is a class type, but it's immutable and it's final. So you cannot inherit from it and change the behavior of a string. And the reason they made it final or made it immutable is just because of security reasons. Including your character string within double quotes will automatically create a new string object. So characters are single quote. You have to only have 1 letter. If I have 2 letters, the compiler will give me a compilation error, because it says that this is not a character literal. Character literal must only have 1 letter, right? A string literal is double quote. So a string literal double quotes. So if I say a string s1 equals hello, right? Then what happens here is that now this is described as a string literal, which means the JVM saves this in a special pool or a special area in the I have a typo here. So JVM saves these string literals or even character literals in a special area of the Java heap called the string pool, a string constant pool. Basically, the string literals are constants, just like integer literals or character literals, right? These are constants. These are never going, the value, the memory that occupies these values never going to change, because these are constant, right? You cannot do anything in the source code. These have to be saved and then load into these variables, or these variables. This is not a primitive type s1. It's a reference to an object that holds or points to the value in the string pool, right? And we looked at the string pool before, I believe, or in other tutorials. So strings have interesting behavior. For example, and the nice thing about Java is that a string class has a lot of very nice methods to work with strings, which very nice. For example, let's say I want to convert this to uppercase, so s1 to lowercase to uppercase, right? sysout s2, and if we run this, it automatically converts all the letters to uppercase. So instead of you to try to come up with how this uppercase is implemented, or try to come up with your own uppercase, and as you can see, it does this basically some checks, but the baseline here is that for English alphabet, it assumes some sort of that number 32-bit integer difference in the ASCII table. It does this kind of things, right? For English, it's very easy to convert to basically uppercase or lowercase. Most languages don't have this kind of support in their alphabet for uppercase letters or lowercase letters. English alphabet has this, right? So an English alphabet letter can be uppercase or lowercase, but this might not apply to other type of alphabets, other languages that UTF-16 supports, right? So when you use this, your string literal can have some sort of UTF character that is not part of the English alphabet, but then to uppercase might not give you any meaningful result, right? String objects are immutable, which means that once created, their value cannot be changed. So whenever you have a method from a string that returns a new string, that string is a new string. And so this S2 reference is not the same as S1, right? Even if you append something to S1, for example, if you say S1 plus world, for example, this returns a new string because the plus operator is overloaded for the string Java types, but then this S2 and S1 is not the same. So hello world, but then if we compare the references, S1 equals S2, compare the memory addresses, this returns false. In some programming languages like C++, if you use so in C++ we use std string, in modern C++, and there are when you append something to the original string, it's still the same object, right? So there's a difference here between Java and C++. The string class is not technically a primitive data type, it's a class, right? It has a class definition associated with it, but considering the special support given to it by the language, which means you can assign primitives to it, which means the assignment operator is overloaded, the plus operator is overloaded. For example, the minus operator is not overloaded. In some languages like Python, the minus language is overloaded, for example, or you can overload it and subtract or remove the characters from the original one. But here the plus and assignment is overloaded. Considering the special support given to it by the language, you will probably tend to think of it as such, which means as a primitive. You will learn more about the string class in section strings. So I guess the next topic is initializing a variable with the default value. It is not always necessary to assign a value when a field is declared, which means you declare it. Declaration of a variable means you just give the type, declare the type, and declare the name, right? But don't initialize it. Fields that are declared but not initialized will be set to a reasonable default. The default value is obvious, and the JVM will definitely, that's a guarantee by the Java, that all the member variables, all the fields of a class that are defined in the global scope of the class will be initialized when the class is loaded. Generally speaking, this default will be 0 or null. So if it's a primitive type, it's all the bits that hold the associated with that primitive type will be 0 in the memory. If it's a reference type, it will be null. And again, if you're familiar with C++, null pointers are just all the bits are 0, but they are not primitives, they are pointer types depending on the data type. Relying on such default values, however, is generally considered bad programming style. So even if you have global variables or fields in your class definition, try to initialize them with whatever variable you think is the best. The following table summarizes the default values for the above data types. Byte is 0, basically all the bits are 0. Line is 0 line, float 0 float, double float, character. So the null character or the 0 character is all the bits are 0, but this is called a null character. And so basically a null character is something like \0. So if I say char C5 is a character, if I say 0, this is still a ASCII, right? So if I do a sysout C5, this is not a null character, so not the null character. This is 0 character, part of the English, alphanumeric English. But if I want to have the null character, typically we just escape the 0, something like that. And this is allowed, so the compiler doesn't allow this. Basically the compiler allows this because it realizes that you don't want character 0, you want the null character. A null character is a character type which has all its bits set to 0. In the ASCII table, a character with all its bits set to 0 is called a null character, which means it doesn't print anything to the console. C6. Nothing. So if I say null character and then plus this, we're converting that null character to a string. As you see, there is nothing here. So null character doesn't print anything. It doesn't move the caret to print. It's not a white space. Note that the null character does not translate into a space. It translates into a space. So if I, after this, if I say h, some character, this h should immediately come after this colon character. Yeah, you see, null character is just that in the console, in the terminal, it's like it's not there, it's nothing. So you never, null character means nothing. And the reason they needed this null character is for, in C, if you're familiar with the C language had the character, the strings were an array of characters, right? Array of characters. The problem was that they wanted, at runtime, when you run your application, you're reading the the characters in the array, you want to know what the size of the array is. So they said they always they define a null character, and then when you have a character array like A and then the next item is B, then the character array continues until you hit this null termination. This is a null character. So when you define a string in a C style way, or assign a string in C to an array of characters, then you have to be careful about adding a null character. Otherwise, you might run into buffer overflow, this kind of stuff, which is very dangerous and error prone. So I hope you enjoyed this very interesting topic on characters and strings. Please stay tuned, and I'll see you in the next one.